A man in Arizona spent $38 in his backyard and built something that outperforms a device the entire HVAC industry has spent 120 years and billions of dollars refining. A sheet of aluminum, some paint, and a bit of copper tubing, and it cooled his workshop without pulling a single watt from the grid. By the end of this, you'll know exactly what he built, why it works, what it costs, and why nobody selling air conditioners wants you to know it exists. Right now, cooling your home off-grid means a window unit pulling 500 to 1,500 watts, or a mini-split still drawing 300 to 700 watts on its most efficient setting. Run that 8 hours a day through a Texas or Arizona summer and you're burning 2 to 6 kilowatt hours daily, just on cooling. That's electricity you buy from the utility at 12 to 25 cents a kilowatt hour, or generate from solar panels that cost thousands up front and degrade about 0.5% every year. If you're running batteries to cover that load, a lithium iron phosphate bank big enough for summer cooling runs $3,000 to $8,000, before the inverter, the charge controller, and the wiring. And here's what should bother you. Cooling is the fastest growing electricity demand on the planet. The International Energy Agency says air conditioning and fans already account for roughly 10% of global electricity use, and they project that demand will triple by 2050. The industry's entire response to that is a marginally more efficient version of the same compressor loop Willis Carrier patented back in 1902. Compressor refrigerant, expand it, blow air over the coil, dump heat outside. Over 120 years, and the fundamental approach hasn't changed. Every step needs power. Every part eventually fails. His panel needs none of that. He took a 4 by 4 foot sheet of 0.02 inch aluminum from a local metal supplier, coated it with 2 layers of acrylic latex paint mixed with titanium dioxide powder, mounted it on insulated plywood backed with foil-faced polyisocyanurate foam, and angled it up at the open sky. His logged readings showed the panel surface running 4 to 7 degrees Fahrenheit below ambient at night, and roughly at ambient during the day once he added a simple plastic film wind cover. He soldered 1/4-inch copper tubing to the back, ran a small water loop through a fan coil unit in his workshop, and reported noticeably cooler air in a space that used to be unbearable by afternoon. Total cost, $38, including the pump. Here's why a painted piece of metal can do that. Everything around you radiates heat as infrared light, your roof, your body, a cup of coffee going cold on the counter even if you never blow on it. Normally the atmosphere catches most of that infrared and sends it right back down and at you. That's the greenhouse effect, and it's why the planet stays warm enough to live on. But there's a specific window between 8 and 13 micrometers where the atmosphere goes nearly transparent. Radiation in that band passes straight through the air, straight through the clouds, and out into space. And space sits at roughly 3 degrees above absolute zero, about minus 454 Fahrenheit. That's the coldest heat sink in the universe, and it's sitting directly above your roof every single second of every single day. Any surface that radiates strongly in that 8 to 13 micrometer band is pumping heat into deep space for free. Bare aluminum won't do that on its own. Its emissivity in the thermal infrared range is only around 0.4, which means it reflects most heat back instead of radiating it away. But apply a coating with high emissivity tuned specifically to that 8 to 13 micrometer window, and you turn the same sheet into a sky-facing radiator that bleeds heat into space continuously. During the day, sunlight dumps about 1,000 watts per square meter onto a surface, which normally overwhelms any cooling effect. That's the part that took real science to crack. He wasn't working from folklore. In 2014, a Stanford team led by Sean Hay-Fawn published a paper in the journal Nature proving a multi-layer photonic panel could stay nearly 5 degrees Celsius below ambient air temperature at solar noon in direct sunlight. Their device reflected 97% of incoming sunlight while still radiating strongly in that atmospheric window. No electricity, no refrigerant, no compressor, no moving parts, while the sun was beating straight down on it. A few years later, a team at the University of Colorado Boulder, led by Xiao Yin and Rongui Yang, published a cheaper version in the journal Science, a glass polymer hybrid film, basically plastic, embedded with tiny glass microspheres that could be manufactured in rolls on standard industrial equipment. They estimated production costs as low as 50 cents a square meter at scale. This physics isn't new or fringe either. Radiative cooling has been observed and documented since at least the 1770s. Ancient Indian and Iranian civilizations used shallow pools of water left out under clear night skies to make ice, even when the surrounding air stayed above freezing. They were exploiting exactly the same atmospheric window, no electricity, no chemicals, just geometry that's worked since the atmosphere first formed. One of Fawn's co-researchers, Aswath Raman, later co-founded a company called SkyCool Systems. By 2019, SkyCool had panels mounted on a grocery store roof in Stockton, California, pre-cooling refrigerant fluid before it hit the store's condenser units. Measured result, a 12 to 20% reduction in cooling electricity. For a grocery store, spending tens of thousands a year on refrigeration, that's thousands in annual savings from panels that draw 0 watts. Separately, researchers in Mendoza, Argentina, tested a much simpler version. Aluminum sheet coated with white acrylic paint loaded with titanium dioxide, a coating anyone can mix themselves. Their panels hit 6 to 8 degrees Celsius below ambient on clear nights, and still manage 2 to 3 degrees below ambient during the day behind a basic polyethylene windscreen. Total material cost per panel, under $15. So why does almost nobody know any of this exists? Because it doesn't produce a sellable kilowatt hour. The federal solar tax credit rewards systems that generate energy the grid can measure and monetize. A radiative panel doesn't generate anything, it eliminates demand, and eliminated demand never shows up on a utility's revenue statement. Carrier, Trane, Lennox, every major manufacturer makes its money on compressor-based systems that need professional installation, annual maintenance contracts, and replacement every 12 to 20 years. A panel like his has no compressor, no refrigerant, no motor, nothing to maintain, nothing to replace, nothing to sell you twice. From the industry's side, it's a dead-end product. You buy it once, and it works. Building codes compound the problem. Most local codes have no category for passive radiative cooling. It isn't classified as HVAC equipment, it isn't classified as roofing, it isn't classified as solar. So when a homeowner asks a building inspector about mounting one, there's no box for the inspector to check, and in a lot of jurisdictions that just means the answer is no. Not because it's unsafe, but because it doesn't exist in the paperwork. Even the mortgage system reflects this. A photovoltaic system adds appraised value to a home. A geothermal heat pump adds value. A passive radiative panel adds nothing on paper because no appraiser has a line item for it, even though it can be cooling the house for free. If you want to build your own version, here's how he approached it and how you can too. Start with the emitter itself. Aluminum sheet, 0.02 to 0.04 inches thick, alloy 100 or 3003, smooth flat stock, not corrugated. That runs $18 to $26 for a 4x8 foot sheet from a metal supplier. For the coating, mix standard white acrylic latex exterior paint with titanium dioxide powder at about 10 to 15% by weight. You can get that powder from art supply or chemical suppliers for $12 to $18 a pound, and 1 pound covers several panels. Apply 2 to 3 thin coats with a foam roller, letting each one dry fully. Even coverage matters more than thickness. Thick globs create thermal bridges that hurt performance. The insulation backing matters more than most builders expect because you need to stop the panel from absorbing heat from whatever's underneath it. Use 1 to 2 inches of foil-faced polyisocyanurate rigid foam, about $15 to $20 for a 4x8 sheet from any home improvement store. Mount the aluminum with the coated side facing up and the foil side of the foam facing down. For a water-cooled version like his, solder or thermally bond 1/4 inch soft copper tubing to the back of the aluminum in a serpentine pattern before attaching the insulation. Run a small 12-volt DC pump, the kind sold for garden fountains about $15, to circulate water through the panel and into an indoor heat exchanger. A used automotive heater core works well for that and costs $10 to $30 at a salvage yard. One warning worth repeating: never use galvanized steel instead of aluminum. Galvanized coatings change the infrared emissivity profile unpredictably, and the zinc layer degrades rapidly under UV exposure once it's combined with titanium dioxide paint, which is photocatalytically active. Stick with bare aluminum or stainless steel if you want it to last even longer. A convection shield matters too, especially for daytime performance. Stretch a thin sheet of low-density polyethylene, the same clear plastic used for greenhouse film, over the panel with an air gap of 1 to 2 inches. That blocks convective heat gain from warm air without blocking the infrared emission in that atmospheric window, because polyethylene is largely transparent between 8 and 13 micrometers. A 10 by 25 foot roll of 6mm greenhouse film runs under $20 at most farm supply stores. The skill level here is basic sheet metal work and simple plumbing. If you can cut aluminum with tin snips, solder copper tubing, and use a caulk gun, you can build this. No welding required, no electrical work beyond wiring a small DC pump to a 12-volt source, which can even be a small solar panel of its own. Now, some real limitations you need to understand before you commit. First, humidity kills performance. In the dry southwest, where he lives, radiative cooling works beautifully because the atmosphere is transparent in the thermal infrared. In the Gulf Coast states, where humidity regularly exceeds 70%, atmospheric water vapor partially closes that 8 to 13 micrometer window, and cooling effect can drop 40 to 60%. A panel hitting 7 degrees below ambient in Tucson might only manage 2 or 3 degrees below ambient in Houston. Second, this is a cooling technology, not a power source. It won't charge your batteries, it won't run your lights, it just removes heat from a surface and rejects it to space. Third, cloud cover matters. Thick overcast blocks the atmospheric window, while thin, high-altitude cirrus clouds stay fairly transparent. Clear desert skies at altitude are the ideal conditions, which is exactly why this works so well for him. A single square meter of panel only produces 30 to 40 watts of cooling effect, roughly what a small desk fan moves. To meaningfully cool a 1,200 square foot home, you'd need somewhere around 20 to 40 square meters of surface. That's about 215 to 430 square feet of panel area, depending on your insulation, your local humidity, and how brutal your summers get. For a home with a decent-sized roof, that's achievable, but it's not trivial, and it's worth sizing your expectations accordingly before you start cutting aluminum. The average American household spends $350 to $600 a year on air conditioning electricity, according to the Energy Information Administration. An array built for under $300 total, offsetting even 30% of that load, pays for itself in the first summer, and it keeps working for decades with no maintenance. Compare that to a mini split at $1,500 to $4,000 installed. Compare it to a home battery at over $11,000. Compare it to a full rooftop solar array at $15,000 to $25,000 before tax credits. This doesn't replace all of that, but for pure cooling, nothing else comes close on cost per watt of heat removed. The physics is over 200 years old. Stanford proved it works in direct sunlight. SkyCool proved it works on a commercial rooftop. He proved it works in a backyard for $38. The only thing standing between you and free cooling is a sheet of aluminum, a can of paint, and the fact that nobody selling air conditioners wants you to know this is an option. So here's the question. Would you spend a weekend and under $300 building a set of these panels, or would you rather put $4,000 into a mini split and the solar capacity to run it? Tell me in the comments. I want to know how you'd spend that money. And if this was useful, subscribing and sharing is the best way to help this channel keep going. Next time, we're looking at a dirt cheap thermal battery that stores summer heat underground and pulls it back up in January. Same philosophy. No moving parts,